Okay, so we're starting in class 12 and we're going to continue with Bernoulli. And this is actually not in chapter 5. We're jumping ahead a little bit, but I think it works well in the context of what we've been covering. And no pun intended, it flows to stuff that we want to know about. And so we're jumping ahead to chapter 8, actually. And this is section 8.8 in chapter 8, 888. And we're going to do with flow meters, an important thing to know about in fluid mechanics. So there are three types of what we could call Bernoulli-based flow meters. You might even say that there's four if we included pitot tubes, which I do have a homework problem where I have a pitot tube. And I'll give away at some point the answer to part B of the pitot tube homework problem if you listen to the videos very closely. So the three types of Bernoulli-based flow meters are the orifice plate. So we have this blockage in the system. It's got a little hole in this plate that's blocking it. And because of the pressure drop across this plate, we are able, from some calibrated curves, because these orifices are kind of standardized, we can find out based on that pressure drop what the flow is with a correction factor. We also have a nozzle. So this is sort of a smoother transition. It's not quite the severe blockage that an orifice is, but it makes this nozzle right here, and the pressure taps that we have off of this are at particular locations away from here. And from this, we can find from the pressure drop, and including some calibration information, some correction factors on top of this, we're able to estimate what the flow is. And then lastly, we have a Venturi tube, which has like pressure ports located in the upstream and then the just downstream of this restriction. And this Venturi, it's a considerably larger piece of equipment, but it is going to be a lot more accurate and less of a pressure drop than the other two. And they all have in common is they're changing between diameters. So we have a parameter we often use called beta, which is really the ratio of diameters, and it's going to be something that's a small, less than 1, right? So it is the small diameter divided by the larger diameter. There are other types of fluid flow meters, and I will touch on them briefly, but not talk about them too long. This measuring fluid flow is a very desirable but difficult task to do in lots of different systems. But you can imagine some of our motivation in measuring the flow is because we might be moving like natural gas or gasoline or oil, things that are pretty expensive per gallon. And we want to be able to measure how much flow has gone through. And that's an important thing just in terms of economics. But we also have like different systems and that kind of thing where we would like to have to measure the fluid flow. The truth be told, though, these we pay a penalty for measuring these fluid flows because there's going to be a pressure drop that we can't recover, a head loss that happens across these things. So this actually falls in the later chapters because we start to dive in closer into the nature of these losses. But I felt it was okay to include them here because in these instances, we just get these losses from various curves, right? So let's see if I have the curves later on presented in here. Let's see, do I have them? Jumping ahead. No, okay, so in terms of my notes, let me go to my notes. And we'll take a look at those curves, the basic ones. I wish I had put them in the slides, so I'll try to remember to put them in. Say we're talking about class 12 here, and opening up these notes. And so I put them in the back few pages right here. So here are the main ones, and of course I have them sideways. So what good does that do me? I'm going to rotate my view clockwise. There you go. So here's the ones. These come from Munson's, and these are curves, factors that we're going to multiply our equation by to get the flow, and they account for the the calibration, I should say. I'm not going to say they're not necessarily the losses, but they, in terms of the pressure drop that we measure from these predetermined locations, these taps on either side of either the nozzle or the orifice or even the venturi, we're able to use these to make sort of a correction. And they have a similar one. Let's see, I'll re-rotate the view here counterclockwise. Similar curves are available in Sengel. They labeled something differently, but so these can be used to do some correction onto the stuff. So what I encourage you to use is the Munson ones. That's what I'm kind of used to, but we'll talk about these some more when we get to that section. So I guess I didn't write this out the way I wanted to make this into an animation, so I'm going to screw it all up by doing it now. And I think I wanted to do this by line, and I think I just messed everything up. I guess I'll go to animation pane. I should have paused this, but anyway, let's see if it'll let me do this all at once. Effect options and timing and on click, and nope. There you go. Okay. So let me talk about this one thing at a time, instead of writing it out on the piece of paper, because I'm tired of writing on the paper. So these advantages, they take these devices, they all are kind of, you can think of them as interfering with the flow, and they take advantage of the pressure drop that happens to evaluate the velocity. So if we take a Bernoulli 1, so I'm calling this Bernoulli 1, and we set of course the height's not going to change. We're going to keep these horizontal. At least in your standard one, we're going to keep it horizontal. We might turn it vertically for some reason, and then might want to necessarily have a little bit of the elevation change, but not really. We're also going to use in conjunction incompressible continuity, right? So the volumetric flow rate at 1 is going to be equal to area times velocity at 1, and the volumetric flow rate at 2 is going to be area 2 times velocity. So we could know that the velocity 1 is going to be the volumetric flow rate divided by the area, and the velocity 2, same thing, true, right there. So we could substitute those in and solve for the volumetric flow rate. Notably, what we were able to do is get rid of the velocity. So we solve for the volumetric flow rate. So here is an equation that's going to be pretty useful to us. But the one that's more useful, and I didn't, so I'm going to write this while we're in class, but we could take this this is an idealized flow rate, but it doesn't actually behave that way, right? So what we'll do instead, something I forgot to mention here. In a piping system, we'll actually see that there's this sort of like a corollary thing where the volume flow rate is related to the pressure drop. And that's what this equation has done. We've got the volume flow rate is really a function of this pressure drop. You can see everything else here is going to be a constant, assuming a constant density right here. And you can see we have this little ratio that's going on. So what we do is we introduce that ratio that we had up above before, right? That ratio is D over D. But now because we're talking about the areas, and the areas are that ratio squared, and now we're going to square it. So we end up with that beta raised to the 4 here in the denominator. So this is our basic equation for any of those flow meters, where we have the CD, which is labeled in some places like CO and CN and CV. What they mean is the orifice, this is the nozzle, and this is the venturi. These coefficients right here are like a fudge factor that we multiply, and they're based on the geometry. So you see there's the beta and these lines, and they're also based on the Reynolds number. And we'll talk about Reynolds number a lot more coming up very, very soon. But Reynolds number is, you could think of it as a measure of the viscous forces, excuse me, the dynamic forces versus the viscous forces. And you can see that the dynamics has a velocity on the top, right? And then it has viscosity on the bottom. So there's a competition. So they're talking about a ratio of those kinds of forces within the fluid. So the faster, the larger the Reynolds number, the more the dynamic forces are overcoming the viscous forces. So really, with a high speed, we get a higher Reynolds number. And so you can see that these factors right here for the have a sort of a trend that are kind of different for the orifice versus the nozzle. And they don't really even give you specific ranges for the Venturi. But you can see just from the range for the ranges where for the nozzle, we have like 0.6 to like 0.64, like in that range right in there. Whereas for the nozzle, it's a lot better because we're sort of in the 0.94 to the maybe, you know, almost to 1. 0.99 it even goes to. Over here for the Venturi, we kind of have this range, at least for Munson, these are the curves for Munson. They don't really give you a specific, right? So I usually draw like a line like right down the middle if I'm going to use this curve right here. Yeah, so and I have larger ones and available at the end of the notes. Notably, though, this is an upstream Reynolds number. Pretty soon we're going to introduce, get more into non-dimensional numbers, and these are examples of non-dimensional numbers, an empirically found coefficient that we can use with a certain amount of reliability and repeatability to be able to predict fluid flow. And we'll see that that's a very common thing in engineering for us. Okay, so also in Sengel, so instead of using those curves, they have provided these equations. So these are, instead of using the orifice or the nozzle graphs, you can plug in the betas right here, and that's a 2.5, by the way. I cut off the top of the 2.5 for some reason. This is equation 872, so you should have the book and you should be able to put in there. So I have the betas put into there, and they have Reynolds number. And and the same thing true for the nozzle. And I actually found where these come from, interestingly enough. So let me see. I'll go over to that website, or I found a source that repeats them. So if you go to discharge, this link that'll be in Blackboard, you could go, you can see the Nutrium. I don't know who they are or what they do. I'm not advertising for them. But if you come down and you can see some more stuff about the difference, you could learn more about fluid dynamics certificate from Cornell University. Oh, this advertisement, that's interesting. If you come down to here, here's where some of those came from. So you can see that they have the orifice with corner taps. This is the same equation that we have right there. Although that says to the sixths. Interesting. I've actually ran across a problem recently. Let's see, we'll go back. Let me go back to this. That's to the 8. I think that might be where we have a problem. Okay, I found a problem in using these graphs, but let me double check that right there. Let's see, that's 0.312 to 2.1. Yeah, and there you go, 0.184. 0.184 to the 6. And then you can also see there's the 91.71. 91.71 over here, and that's the beta to the 2.5. And if you look up above, they have the Reynolds number raised to the n, and you'll see over here, here's the n, right? So this has some other stuff onto there, but you could also see that they match up this orifice at the corner taps. And then lastly, we have the nozzle meter. But that one was a little bit different too, right? So that's got 0.9975. Here you go, the 0.9975 minus 6.5. There it is right there, right? So go to this. You go to this website. You could find the same stuff, but this is in Sengel. And let's see. I do this quite often, so I'm riffing right here. But I make a lot of things in Excel and test some things out. So this was homework. This is homework 6. If you look really quickly as you go through here, you can see what the answers are. But I went ahead and I took a look and superimposed for the orifice right here. It's kind of hard to see, so I'm gonna move this over to the side. I superimposed a graph of those equations on top of this, and I got a weird answer right here for the 0.7. It didn't correspond. But let me fix that one thing. That was a 6 right there. Let me see if he gets better. So I'm going to go over here and let's see if he improves. Nope, he got worse. Son of a gun. I can't figure out why 7 isn't working as well as I expected, right? So superimposing these on top of each other, you can see that we have a pretty close correlation. Like I made this, so the corners right here match up and all the grids matched up. But it starts to deteriorate. Like 0.6 ain't so great, but 0.7 is terrible. Like I don't know why, and I can't explain to you why those are different. They should be the same. I found many books have this issue where they have these graphs and they have equations and they don't match up with each other. I will mention that the nozzle looks like it's pretty good right there. So you can see the nozzle when superimposed on top of each other, matching up the graph. The two that we could trust these equations are pretty good, but I'm a little skeptical of this graph right here. And to make a complete set of these graphs, I'd also point out that Sengel has, let's see. Okay, so I found it under, see, I'm going to go into the Venturi meter. They have this graph right here. So this is figure 643. I think this is, no, actually this is out of another book. I'm sorry. So I've included this one. I believe I've included this one in the back of your notes. So take a look at that. Take a look for that. Yeah, this is from Frank White's Fluid Mechanics. Okay, so here is one that you can maybe use for the Venturi nozzle, but I think in the homework problem, I've actually given you what to use. And 0.9, a lot of people just use 0.98 for the Venturi meters. I'm not 100% sure why they're saying to use this one, because they have an additional one right here to use for the classical Herschel Venturi, and so you have Reynolds number right in there, and you can see they have the long radius nozzle. So they're comparing the two things on here, but this dotted line, dashed line, it looks like it actually has better than this one right here. So anyway, I think my video went longer than I intended it to go, but we introduced these ideas of using this equation with this factor. Only things I think I would add before doing more examples. Do I have more that I want to talk about? I did have a little bit more. Okay, so we're going to have some pressure drop that happens across these meters, but we can recover some, but there's going to be some permanent loss. This fraction of pressure loss that we're going to get. And that's, you can see from this figure right here, this is from Sengel, that it's dependent on that ratio, that beta ratio, the D over D. And the orifice is the worst one. The flow nozzle is better, but the Venturi is much better, right? In terms of like the fraction of the pressure loss that you get. So this is it Heisenberg's principle, or I'm butchering it, I'm sure, something along the lines of the act of measuring something will unfortunately influence the outcome. That might be Occam's razor. It's one of those razors, one of those rules. I don't need to remember that kind of thing. You can look it up. But it's the general concept by because the act of measuring the thing actually influences the results. This is a classic example because you're getting in the way of the flow. So there's lots of other flow meter types, and this is already a long video, so might as well go in for it all. This has to do with the compressibility effects. I put these in your notes, copied directly, just to say that there is a bit of a correction factor that they've attempted to put in there. Once again, this equation that I got out of Krohn-Elger's book, it does not correspond with this thing that came out of White's book. I don't understand why that's not true. But it's a fact, right? This compressibility, or as they're calling it, the expansion factor, that I tried to make a problem where we adjusted for this or looked for it, and it didn't work out so well. So it took me a little bit longer than I liked to write these homework problems because I was trying to make a good usable use of this, but I'm kind of frustrated by the fact that this graph doesn't match this equation, although it's supposed to. Here's some examples I'll do in the next videos to come. Here's some flow meters. I have a lot of experience with this one right here, where you have this like rotating vane inside here, and this is a very, very common type of flow meter. And there's like a little metal nub that's on this rotating turbine here, and there's a magnetic pulse, and it picks up and kind of gets the RPM, and then there's a calibration curve used on there, but this will estimate what the volumetric flow rate is. It's very, very common. Something I should have pointed out that I didn't is the fact that when using any of these flow meters, you really want a long stretch of straight pipe before and after the meter. It's kind of an important thing because you want like a nice uniform flow before it gets into the meter, and you want a uniform after the fact, which I think is always interesting. And they usually measure that in number of diameters ahead of the flow meter and after the flow meter. It's kind of an important thing in the practical use of flow meters. Pitot tubes, we'll talk about. Do I have an example? Anyway, I said that I was going to bury this somewhere in there. The reason why the pitot tubes aren't a great measurement for flow is because they really are good for measuring local velocity. And as you'll recall from some of the first class of the semester, we mentioned that when you're in a pipe and you have a velocity flowing through here, we kind of think of it as being uniform across here, but we have that idea of the zero slip location. So we actually have a developed velocity profile that's distributed like this right here, where the velocity in the center is going to be larger, right? So when we have a pitot tube, and hopefully it's a long, slender pitot tube, so it's not disturbing this too much, we get a stagnation pressure. That's really going to measure the velocity at the center, which is not indicative of what the velocity across the whole thing is going to be in most cases, right? Especially as you get to be a large duct or something along those lines. Pitot tubes are much better for gases, I think, than for liquids. And so there's some vulnerability about what's happening in and around here, but it's a pretty accurate measure. What you could do is you could have maybe multiple pitot tubes, like you could instrument the thing, and you could capture what the velocities are, but of course the act of doing this will also influence the results of the thing. But if these are small enough, maybe they won't be too bad. And you could get you could maybe try to figure out what this velocity profile would look like if you were very careful in your instrumentation. But the big weakness of this is that we're only getting the velocity at whatever location we have that pitot tube, whereas these other flow meters are actually designed so in conjunction with these calibration curves that they set up and account for the distribution of that flow across the pipe section. So that would be the answer to that second part. And I made a 24-minute video. Now I'm going to keep on going. Right? Why not? Okay, so we have here's the pitot tube and a close-up of the pitot tube. That's a nice one. These are all Sengel slides. And by the way, don't ask me to post the slides if you're a non-UHeart person. I don't own these slides. I don't have permission maybe to give them away, but I am like showing some of them. But I'm also giving attribution to Sengel and advertising. Buy his book. Yes, that's what I say. So anyway, these are, you know, discussing these other, but here's some different flow meters. Okay, so here's some of these interesting types, and I appreciate being allowed to use these images right here, and you can see that we have this pressure tap on the bottom and the top, and there's like a bellows, and a magnet, and that's for this flow cat. That's their method of doing a flow meter. Here's one of positive displacement flow meters. This one I'm not sure if I've ever seen this, but this is a very common one. This nutating disc. I like the name, the nutating disc. So I think a lot of if you have like city water and you're getting there's a water meter reader. This is the type of meter that you use, and so this disc looks like kind of like Saturn, kind of like it's kind of like rotating on its side, but its rotation will be it knows for every rotation that it makes how much what a chunk of water or whatever you're measuring that goes through there. So it's like we consider that a positive displacement. That's the name that we give when except for the leaks that are going to leak by, inevitably they're going to leak by, it has to rotate for every chunk of water that goes through. This looks like a positive displacement pump to me, honestly, these lobes. So there's a double helical, so this is a positive, this is a flow meter, but I tell you what, I don't know if those don't look like they would rotate very easily. But there is such a thing as a positive displacement pump where there's a gear drive that makes these lobes turn. And I've seen that like a roots blower type of thing. But this doesn't look like a flow meter to me. And here's another picture of the nutating disc from another source to give you sort of an idea. And there's like little gears, and it'll measure onto the little dial right up there. So the turbine flow meters, I mentioned these already. Once again, okay, so this is another type where it's actually going to have a magnetic impulse that's going to be picked off of the blades as they pass the magnetic field. Here's like a paddle wheel. Never seen one of these before, but it's kind of a funny looking thing. It looks like an old paddle wheel. And you need a calibration curve for every one of these things, by the way. So they set them on a test bench, and they measure the amount of beats that are going through there, and then they know what the fluid flow, and they create a calibration that you're supposed to use in the electronics pickup for these things. Here's one that's an interesting one. It's a variable area. So this is a very cheap one. Doesn't require many moving parts, but this actually operates on Bernoulli principle right here, where you got the flow around. The faster the velocity that's acting around this thing, the higher this thing will reach upwards. So you have the scale that you can read off on the side. Obviously, you can't have too high a pressure because these things are made out of plastic. But there's a spring-loaded one as well. It's a cheap way of trying to measure flow. I like the name rotometers, by the way. There's also crazy thing. The ultrasonic flow meters had tons. I used to have tons of. Back before the internet, we used to call up and ask people for their literature. And the ultrasonic flow meters, they love to do this, where they're bouncing waves off of stuff. And this one goes on the Doppler effect. But there's other ones that rely on hopefully there's some kind of disturbance of like particles and stuff that they can have, and it really needs some kind of amount of disturbance. If it's too slow and too clean, you can't actually measure the flow. But the great thing that they like to advertise, it's on the outside of the pipe, and it doesn't interfere with the flow. It'd be really great if these worked well. But the guys who sell them, they'll tell you that they do. So I don't know that to be true. It's one of those things where you really have to make sure it's the application specific, and the calibration of it is going to be the most important thing, I think. But there's other types. I'm just going to mention that there's all kinds of various types vortex things, and I think the vortex actually measures based on the Struhal effect. We'll learn about that soon. Well, when you create a vortex, it creates a natural frequency, and if you could pick up what that natural frequency is, you're able to maybe work backwards and figure out what the velocity is. Oh, I thought this is a very cool one, and this is for gas flows. It is like a hot wire, and don't ask me how they work, but you could get a handheld one of these and do a pretty good job of measuring the flow velocity. It's about really the heat exchange across this hot wire, and so you can figure out how much current is drawn to be able to maintain a temperature, and based on that, you're able to work backwards and figure out how much velocity of air usually going past the thing. Or it could be other liquids. And I'm going beyond my expertise in any of these. Just know that there's lots and lots of different ways people have attempted to quantify how much flow is happening in something. They're very motivated because for a very good reason. There's a financial motivation, but also from an engineering perspective, we want to know what the flow is. And it's a very difficult thing to measure accurately and reliably, especially without interfering with the flow itself. So that was way too long of a video, but it had a lot of information in it, so maybe that's fine. I'll do the examples in the other videos.